As we continue to go into Chapter 8, the first section we looked at similar polygons. Now we're going to just narrow it down, and we're just going to talk about similarity in triangles. So our first one we're going to be looking at is similarity by AA, or angle-angle similarity. Some of these, as we start to go through them, they're going to sound kind of familiar, because this kind of sounds like when we talked about congruent triangles, the minimum kind of information that we needed in order to prove they were congruent. Now we have a minimum amount of information we need in order to prove that the triangles are going to be similar to each other. So if we look at angle-angle similarity theorem, it tells us if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are going to be similar. And basically what happens in this is also think about if I know two triangles already, the third triangle, based on third angle theorem, we automatically would know as well, okay, because all three of them add up to be 360 degrees. So this third angle would also be congruent with each other. And so all that's happening is the sides are just getting longer. The angles aren't changing at all, but this triangle is just getting bigger. And so like if I drew one out here, it would follow the same kind of pattern. We could draw it even larger to where it's just the same triangle, but our angles are just staying the same, but our sides are just spacing out more and contracting in, going back and forth to make similar triangles. So if we look at this first example, it says determine whether the triangles are similar. So we look at it, we have two right angles, okay, so that part we can see. And then we have an angle in each one, so we can always solve for our third angle by doing 180 minus those two other angles added together, so I have 90 plus 64. And so when we simplify that, we get 180 minus 154. And so it would leave us with 26. So if I plug in 26 degrees here. So if you notice now, I have we have our right angles. Right angles are always congruent, so I have like the measure of angle D is equal to the measure of angle G. Okay, so I can make the statement that angle D is congruent with angle G. And now, because I found the other 26, measure of angle K is equal to the measure of angle C, which means that those two angles are going to be congruent as well. So if I have two angles that are congruent, looking back at my similarity theorem, then I can say that those triangles, it says if I have two angles that are congruent, then I can say that those triangles are congruent. And the biggest thing to state here whenever we're showing that they're similar, not congruent, I'm sorry, is that we need to be sure that you line up the same angles in the right order. So if I do triangle, let's say we do this one as CDE. Okay, C we said was congruent with K in this statement. So that means that if C was my first one, then that means that K has to be my first letter of my other triangle. D's in the middle, and D we said is congruent with G, so that means G has to be in the middle. And then that would leave E has to be the same as H. So this would be my congruent statement because of angle-angle similarity theorem. It's my similarity statement, I'm sorry. My triangle CDE is similar with KGH. As we look at example 2, it just says show that the two triangles are similar. So if we look at the first, give us a similarity statement already. We just need to be able to show why we would know that's true. So first in this diagram, you can see we have two angles that are both 52 degrees. So that means we have angle B is congruent with angle C. But in order to use AA similarity, we need two congruent angles. So notice if I look at just my outside triangle, okay, this outside one, and then if I look at my inside triangle in a different color, if I were to separate these out, I have triangle ADC, and then I have a smaller triangle of AEB. Notice that they both share this angle of A. Okay, so if they share it, that means that angle A has to be congruent with itself. Okay, and that would be your reflexive property. And so if I'm able to show that those two angles are congruent, then by AA similarity, they're similar triangles. Okay, and that's all we would need to do for a problem like this. We could do this as a proof as well. This is just kind of a short version of a proof. But I would be able to start off with my given and then doing, like I said, reflexive property and then making this last statement. And my reason would be this last part, that AA similarity would be my reason. In the second one, we have SVR is similar with UVT. Notice in this one it gives us parallel lines. It doesn't give us any angles that are congruent, but it does give us parallel. So the first thing you can notice from this triangle is we have intersecting lines, and remember that angles that come off of intersecting lines are always congruent. So that would mean that we have angle SVR on the left side, that would be this one on this side, would be congruent with angle TVU. So that's the first statement we can make from it. And then think about this line being these parallel lines, okay, being cut by a transversal. Okay, and we always have our angles that come off of our transversals. Those are our alternate interior angles. And those two angles are always going to be congruent as well. So I'm going to have these two angles here. And so that means I can make the statement that VRS would be congruent with UT or VTU, either way. And the reason we would know that would be alternate interior angles. And so then, just like the last one, once I'm able to show two angles are congruent, then by AA similarity, I would be able to show that these triangles are similar. So the biggest way that we use these kind of similar figures, especially in triangles, is we use them whenever to try to do indirect measurement. So in this example, we have a flagpole casts a shadow that's 50 feet long. At the same time, a woman standing nearby is 5 feet 4 inches tall, and she casts a shadow that's 40 inches long. And ask us to how tall is the flagpole to the nearest foot. So we use this based on our triangles. Okay, if we were to draw over here, we have two triangles that have they're similar in the sense that, for one, they're standing at 90-degree angles. Okay, we can know that they're right now, they're standing perpendicular with the ground. And then the sun, wherever the sun is, and obviously it's on this side somewhere, its angle is going to be the same on both of those. And we will end up talking about that again later, but it has what we call a depression angle. And so it casts this light off this flagpole at the same angle that it casts light off of this girl. Okay, so we know that these angles would be the same, this angle and this angle. And then, like I said, then you could say one, it's also the angle coming off the sun would be the same on the ground. Or, like I said, these people would be standing perpendicular with the ground. So we would have right angles in there. So if the flagpole casts a 50-foot long shadow, and the girl, it says, casts a 40-inch long shadow, and she is 5 feet 4 inches tall. So the first thing we want to do with a problem like this is we want to get it all in the same type of measurement. And what I'm going to do with this kind of problem is I want to switch it to inches. I don't want decimals. So I'm simply going to change it to inches. So if I look first at her 5 foot 4 inches, well, 5 feet each has 12 inches in it. So this would be 60 feet and 4 inches, or 60 inches and 4 inches. So together, it makes 64 inches. And then my 50 feet at 12 inches each would give me 600 inches. Okay, so now that I have it all in the same thing, I can say that her height of 64 inches would compare to her shadow of 40 inches. And this would equal the flagpole's height over the flagpole's shadow. So now all I have to do is I cross multiply and solve. So I would end up getting 40x is equal to 38,400. Divide that by 40. And I get x is 960 inches. It does ask for the nearest foot, though, so I'm going to divide it by 12 to try to convert it back, and I get 80 feet. Okay, we will have a lesson over this in class where we're going to be doing some indirect measurements. not by shadows, but with mirrors. But this is also going to be a way that you need to focus on with these shadows, because there will be an extra credit project coming along as well.